Good morning, everyone. My name is Reza Taghavi, and thank you for joining us in this webinar that is organized for the launch of KubrixGEO version 14, the latest version of KubrixGEO, a CAD-based automatic and now interactive meshing software. For those who are new to the area of mesh generation, a slide that summarizes the reason why meshing is an issue to begin with in the area of computer-aided engineering, and in particular in our area, is that in the past, most applications in geomechanics were often characterized by their physical complexity in terms of the constitutive laws and the type of boundary conditions and so on that needed to be used. But today, especially in the last 10 years, we see more and more a complexity due to geometry. So shapes vary, the physics somehow remain the same, albeit complicated. And so these different shapes are obviously fed into analysis models in the form of grids or meshes. As analysis programs such as FLAC3D and 3DEC become faster, then grid generation, which was a very mundane task in the computer-aided engineering task, emerges as a bottleneck, becomes a major obstacle in the speed of things. But recently, as grid generation technologies have advanced, another aspect of the human-machine interaction is becoming more of a bottleneck, and that is the CAD and geometry collection, cleanup, gathering data from various sources, various programs, and so on that emerge as a bottleneck. So what is KubrixGEO? One slide that describes this is that, well, KubrixGEO is a software made of several options or modules. It's an ITASCA product. It's designed to handle complex geometry problems. So it's an ITASCA software where the grids are generated outside of your traditional ITASCA analysis software, such as FLAC3D, 3DEC, or PFC3D. But those grids are readily read into the ITASCA software. This distribution of tasks between a grid generator and an analysis program is somehow the result of a natural evolution that has occurred also in the other areas of engineering. It seems that it's a task that can be easily separated from the task of the simulation process. KubrixGEO also works in concert with the CAD program, in this case Rhino, but it could be really any CAD program. It could be really any type of geological modeling software. And working in concert with the CAD program is important because the geometries are never perfect, and as a result, modifications have to be made to the geometries. And they have to be made to the geometries at a stage where they're most easily modifiable, and that is when there are surfaces, before they become zones or before they become blocks. And a good program to do this modification, obviously, is a CAD program, and Rhino is sort of our favorite because of certain accessibility and ease of use and cost. So cooperation with CAD allows for being able to constantly modify the geometry, then push a button and generate a new model. So why Kubrix with Rhino? Because grids are volumes. Volumes are defined by surfaces. It's easier to work with surfaces than with volume. So in Rhino, you import your geometries in various shapes, triangulated surfaces, wireframe lines from DXF, contour lines, all sorts of means, points, or you even construct your geometry within Rhino. You edit the surfaces, and you create one nice surface that you hand over to an automatic mesher, which understands what this surface is, what the interior of the surface is composed of, and fills the inside of it with a mesh. That's the sequence of operation. Surfaces are defined in some CAD tool, Rhino. Once the surface is identified and clearly defined as a closed surface, which may have multiple volumes inside it, the automatic mesh generation program understands what we mean by mesh here and meshes it. What is the auto-meshing workflow? And there are variations to that, but I've summarized this as read CAD into Rhino, in our case, or build your CAD in Rhino. Clean it up means add, remove, trim, throw away pieces, reconstitute other pieces. Create a closed surface and export that surface in a certain file format that is an industry standard. We use the STL file format, but KUBRIX can read all sorts of file formats. Then run KubrixGEO to build grids, a grid for Flag 3D, or what we call a grid for 3D, which is really a grid of blocks, which then 3D will further discretize into 3D zones. There is also another way of generating these models, which is really started within Flag 3D through the use of the gen command, which allows you to create essentially not zones layer by layer and block by block, but blocks of zones as mesh blocks, block by block. And it provides you a way to identify the corners of these blocks and how many you want in this direction and how many in the other direction. We will talk today about interactive meshing in a slightly different way done within the CAD program, but it essentially is about reading a reference CAD in Rhino. Reference CAD meaning a sort of an outline of what it is that you want to model. And then within Rhino, using that reference CAD as our reference, build an assembly of solids. These solids will basically be hung onto this reference model. Their corners will be placed there, and their edges will be sort of hung there. And once these solids are prepared, at the push of a button, the solids are being turned into a mesh that will be read into Flag 3D. What is Rhino 3D? For those who are not familiar with it, it's a solid modeler that creates, edits, imports, and translates curved surfaces and solids. It supports polygon meshes and point clouds, in addition to the notion of solids and surfaces, which are really mathematical definitions, formulaic NURBS definitions as opposed to collection of triangles and so on. Includes many cleanup tools and many ways of creating surfaces, going from contours into surfaces, taking very, very fine meshes and turning them into coarser meshes, smoothing surfaces, and many aspects of the cleanup process, which involves finding out where are little triangles that are hanging in the middle of the air, or holes in the geometry, or missing parts, or multiply defined surfaces. What's nice also about it, which is really a hallmark of geomechanical applications, is very large meshes. Meshes that could easily exceed several million triangles that you need to be able to cut and rotate and move around on a short notice and quickly. It has a very short learning curve. It's easy to learn. It's well designed, very smartly designed, easy to learn. It's well documented, but rarely we use the documentation. It's inexpensive, about $1,000 in the US and around 1,000 euros in Europe. KUBRIX and Geo are integrated with each other in the way that there is a icon that appears on the top, the KUBRIX icon, in which you will find all the KUBRIX-related commands, and KUBRIX may be launched from within Rhino, but that doesn't prevent it from being launched from any other application. KUBRIX is available within Patran, within SimLab, within Alter HyperMesh, within or can be run independently as a command line option. What are the features and benefits? The features are interactive hex meshing, block structured hex meshing. I'm going to show some pictures. Unstructured test mesh, octree meshing, hybrid test meshing, convex blocking, being able to handle multiple intermittent fractures, local mesh refinement and integration with Rhino. So examples, this is interactive hex meshing. As you can see, these meshes look very different from your typical automatic hex meshing. These look like handmade meshes because they are handmade meshes. This is a novelty in KubrixGEO version 14. I will emphasize this a bit further later. This is block structured meshing, which at first sight is not very different from the manual meshing. We wish we could have an automatic hex meshing that produced meshes as attractive as the ones produced manually. These meshes were produced by KUBRIX hex meshing, which is really one of the few automatic hex meshing meshes that are available, but it's not ideal. It doesn't work all the time at all. For some application it does. For other applications it doesn't. In this case, you can see, for example, that in this example, we have a liner, some sort of a thin area around this shaft, which has been meshed with 3 layers of zone in all across this area, but really meshed with just one zone layer. This sort of behavior is an automatic behavior that we could control to some extent, but at the price of an excessive number of zones, or because it is not automatic, well, we don't have much of a control in terms of the trade-off between zone numbers and zone quality. Unstructured hex meshing, this is a really powerful tool. Tetrahedral meshing is a very easy way to mesh, but certain applications, especially those involving nonlinear, such as plasticity, computational fluid mechanics, some electromagnetics applications, and so on, do not like tetrahedral meshes. We use what we call poor man hex meshing, which consists in taking every tetrahedra in a certain area, in this case in the neighborhood of a tunnel that we are interested in, turn every tetra into 4 hexahedra. So these hexahedra are really ugly hexahedra for most finite element applications, but for FLAG3D, which is really some sort of a finite volume, we call it finite difference, we don't have a very good name for it, but for FLAG3D, they are really not a problem. The valence of some points are very high, so at other points their valences are lower. Surfaces are often very warped, but again, since FLAG3D will subdivide these things into tetrahedra, those do not necessarily come in. So we have been quite successful in generating meshes by this method. So this is what we call TET hex meshing. Octree meshing is one that uses, exploits the fact that geometries that we are using in geomechanical applications are not necessarily, they're not exact, they're not God-sent geometries. There could be, 1 or 2 meters apart. So, well, we don't really need to perfectly match the geometry. So this sort of step-by-step approach of coarse zones that become finer and finer as we approach a certain detail is an acceptable and a very efficient and extremely fast way of generating models without needing even to clean up the geometry. The object does not need to be closed. It would have overlapping gaps and so on. Hybrid TET has octree meshing. So essentially this means that you can combine all the previous methods together, and you need to do that, obviously. You need to do some patching and sewing, essentially, of these types of grid. And that is, of course, possible through the use of Rhino and KUBRIX in parallel, which allows you to take, for instance, a legacy mesh that is made of, say, Cartesian elements or octree elements, and place within that model a very detailed new fine structure and make sure that they all connect with each other. And this all also with the help of the attach command within FLAG3D. Convex blocking essentially means creating convex blocks, and the simplest convex blocks are tetrahedral blocks. So essentially, it comes down to creating coarse tetrahedral blocks. This is the basis of what we need to do for 3D. And then handling, many intersecting faults and so on. And these are examples of those. You can compute and intersect faults. And of course, then what happens is that obviously once you have one single fault hanging in the middle of a domain, you really have just one volume, one group, say, in your FLAG3D model, and it's always difficult to recover. So where are the interfaces, for instance? But KUBRIX transmits to FLAG3D through a face group, which is one of the new capabilities in FLAG3D 5. And it passes to FLAG3D the faces that are to become interfaces. So it makes life very easy. And then local refinement, you can always, this is an example of a pit where the mesh was produced in a tetrahedral way, and in a similar way as to the one I showed earlier for the tunnel, the mesh has been refined into hexahedral meshes in the neighborhood of the detail. Here is another interesting example on the left. It's an example prepared for a rock flow analysis for 3-deck. These are independent little blocks here that you can see maybe more or less clearly on your screen. But we needed to produce tetrahedral blocks for this 3-deck model that have all exactly the same size. And there's a procedure available, and there's a paper that was made at some point that shows exactly how to use KUBRIX and Rhino to produce exactly a prescribed distribution of blocks according to a spatially defined field. So, and Rhino and KUBRIX are integrated, as you can see. The KUBRIX toolbar appears in here. So this KUBRIX toolbar has 5 commands in it. There's the KUBRIX command, launch KUBRIX command. This is the colorize command. Anything that you have selected will be colorized in different colors, so you can easily distinguish it. This is the merge BRFs. That's basically the join command in Rhino, but made for non-manifold objects. This is the new command called BlockRanger within the KUBRIX toolbar, and this is an automatic model generation for a manual model generation for 3-deck. Okay, interactive meshing with BlockRanger, which is, apart from the addition of numerous improvements to KubrixGEO, the previous version of KubrixGEO, one of the most attractive aspects of it is interactive meshing with BlockRanger. So essentially, interactive meshing with BlockRanger consists in get your CAD data, make a series of so-called solids in your in Rhino, and these solids all become mesh blocks. How do we do that? It's done in this way. First of all, let me talk a bit about the benefits of BlockRanger. Well, you get more control because you specify where your mesh blocks are supposed to be, what their orientation is going to be, what their size will be, and how well they will match a certain boundary. Command-based meshing, like the one, for example, that is in the old version of FLAG3D, is slow and limited. And also it's limited to simple curves. Curves are just straight lines or arcs of circle. And as a result, it's limited. KUBRIX's auto hex meshing is not a silver bullet. The examples that I showed you earlier are the examples that worked. And for every example that worked, there's an example that doesn't work. And what do you do then? And there are certain applications, such as civil engineering, tunneling, nuclear waste disposal, mechanical design, that really require control. And control means that I am ready to spend a few hours more, but get a quality of a mesh that is acceptable and undisputable. One of the other benefits of Rhino is that it's extremely easy to learn. If you know how to use Rhino, you're just about a few minutes away from learning how to use BlockRanger. And that is done to the fact that in Rhino, you just build solids. And if you know how to build solids, you know how to generate these meshes. These solids have some restrictions to them, and I'll discuss that a bit later. How does BlockRanger work? Basically, you fill the volume that you want to mesh with certain types of solids. But these can be very different solids, but they have to have 6, 5, or 4 sided solids. So these are solids that kind of look like a deformed cube, a deformed prism, or a deformed tetrahedron. But each of the faces could be a very complex surface. It could be a whole topography, or it could be a lofted surface. Once you have created this assembly of solids in Rhino, you select them, and you click on BlockRanger, and BlockRanger proposes a certain, basically three non-dimensional numbers. One is the maximum relative zone size, the minimum resolution of your model, and the target aspect ratio that you want to reach. The aspect ratio is a little bit more controversial, the way we compute it and the way it is defined. It can be a very severely restrictive parameter, so it should be used very wisely, as if the aspect ratio is diminished, the number of zones may explode. But that is also available. BlockRanger picks it up from there. Basically what it does is that it takes the solid, it validates the model at several levels against tolerances, rebuilds edges, surfaces, solids to spec, reports problem. It's intelligently designed so that when it runs, when it's completed, it signals what are the blocks that have problems. It leaves those blocks on the screen as highlighted elements, so you can hide them. And at that point, you can look at the blocks and say, explode them. And if they're 6, 5, or 4, they should be good. If they are 8-sided, you should explode them and see why they're 8-sided. Each face, you can look at them. Each face should be either 4-sided faces or 3-sided faces, either quadrilateral-like or triangle-like. But their edges don't need to be straight lines or arcs. They could be very complex curves as long as they're defined by one equation. These are NURBS equations. So they cannot be, for example, 3 polylines. If they could be 3 line segments or 3 sort of complex curves. And then a grid is produced for Flag 3D. So here I'm going to show you a very simple example of just a box, which will illustrate very quickly how BlockRanger works. So I start in Rhino. I create a box, an arbitrary box up to here. And now I have a solid, which they call extrusion. I click on BlockRanger, and BlockRanger brought up some parameters. It ran a bit faster than I wanted to, and I read that file into Flag 3D, and this is what it looks like. Let me go to the next example. This is creating a tetrahedron. Again, it's very simple. Within Rhino, I create a tetrahedron. What is nice is that a tetrahedron is a tetrahedral-like solid made out of triangular surfaces. So this tetrahedron, I select it. I click on the BlockRanger command. BlockRanger will give me some default parameters, which I agree with, and that produces, I change the maximum resolution from 3 to 10. And now it produced a file called blockranger.flag3d that it puts in my current working directory. And I now read that in Flag3D. So far, nothing terribly complicated. You can see there's a pattern to this mesh because it's a tetrahedral mesh. Next, I'm going to create a cavern. This cavern is a bit more complex. There are a number of contour lines. First, I'm going to read as a DXF file. These contour lines represent these 3 salt caverns. These are underground dissolved cavities that are produced by water throughout many centuries. So I'm going to hide a few of the other ones, and so keep this one. And I'm going to create a model of this. You can see it's not a trivial geometry, but it has definitely a direction to it. It's sort of kind of like a cylinder, right? So I automatically use the Rhino surfacing tool called Loft, which produced here for me this surface representation. I use it very carefully using an approximation of the curve. And so you can see there's a seam to it. The seam is basically this purple little line here. So I'm going to cut this. If I want to make it into a cube, I need to cut this in such a way that it becomes 4 pieces, but this will be one of the pieces. So one of the seams. So I'm going to split this solid, this surface here, along now an opposite one, and then I need to put this cutting in certain areas so as not to produce very distorted zones. And because this is manual meshing, so you have got to be careful where you cut your object. Exactly the same sort of reflex you go through when you create this mesh either in Flag 3D using Gen command or using IconCFD or using HyperMesh or using FEMAP. Now you can see that this surface has been broken down into 4 faces, and now I say just join them all together and cap it. So now this object has really 6 faces. And so it's a candidate qualified for BlockRanger. I click on the BlockRanger command. BlockRanger will give me a number of parameters. I say the minimum resolution, I want it to be 5 instead of 3. And I say go ahead, and it produces the maximum relative zone size. I also change that one. And it produce the mesh. A flat 3D mesh was generated. And we can read this mesh using the grid import within Flag 3D, and this is what we get. This is now the outside of that same mesh. Again, now I put a box around it. So we have clearly the inside of the cavern is well defined, but the outside of it needs to be subdivided into some cubes and so on. Obviously you're familiar, with other mesh generations where they use 2.5D extrusions for the outside. So this is a very primitive type of meshing, which is what people used to do maybe 20 years ago. But the next version of BlockRanger, which is about to, which will be released, I would say, within a matter of a few months, will have 2.5D extrusion, far better than what the competitors can do, because it is done really truly within CAD, and CAD is not going to be an afterthought of mesh generation. It's going to be coming from CAD, and it will have a user interface as easy to use as this user interface we are showing you here, and it will have exactly the same type of commands on the screen. So it will be actually one of the most advanced automatic, interactive automatic meshing tool on the market beyond geomechanics. So here I showed you while I was talking that this object can be subdivided. The outside now has been subdivided into a number of blocks. Here I'm showing how I move around one of these scenes which I wasn't very happy with, so that I don't create too much of a bad quality sort of zoning in the factory model. And finally, I move on here. And so what I'm doing here is that I'm creating 1, 2, 3, 4 blocks. There's some good tutorials for that. There's some good video tutorials that we will be putting up on how to learn BlockRanger. We just completed 2 BlockRanger training sessions within ITASCA, and a typical BlockRanger training session takes about 2.5 to 3 hours. And after that, you're ready to go. Of course, you still have a lot to learn, but it allows you to, it really gives you a completely different new tool in your quiver for generating models that really do not require automatic meshing and are made of a relatively acceptable, relatively small number of blocks. So, and so on. I will, we can continue to carry on with this. What I'm doing here is that I'm creating these various blocks here. I'm assembling the various surfaces, and this is kind of a detailed live tutorial here. And the net result is a Flag 3D mesh that you can directly read into Flag 3D. Now that I've created basically 1, 2, 3, 4 surfaces, poly surfaces, I now go ahead and cap these things into 4 solids, and I'm then able to create, that will have my 5 solids, including the inside of this model, to cap. So I'm showing here the 4 solids I created around. They're not really solids. The top and bottom are not capped. I've colorized them. They just need to be capped. But since their cap is perfectly planar, now we have totally created 4 closed solids. They all comply the BlockRanger requirement, and there's this outside part as well. I decompose this object like this, I guess, just to show that you can do that in multiple ways. At any rate, I will move on here. So this is the end result of what the Flag 3D model is going to look like. I'm not going to go through that. As you can see, because I chose these blocks to be prismatic blocks, the block decomposition has been done this way. And of course, these are hexahedral blocks, so hexahedral-like blocks, so the mesh will be hexahedral-like. As you can see that the tetrahedral blocks and the hexahedral blocks communicate with each other. There are no dangling nodes in between, so there is some intelligence in there, but things are made designed in such a way that it appears so easy that you wonder sometimes, so exactly what is happening. Another thing that is very nice is that if you, within Rhino, decide to put these different blocks in different layers, well, those layers will appear as different groups in the Flag3D model. And they all will go into the slot 1 of Flag3D. And the actual blocks go into the slot 2. So you can, within Flag3D, go and edit these blocks if you want to. And also, you can organize your model completely in terms of the various excavation sequences or various components of material or geotechnical units. And those will appear as groups within the Flag3D model. Here, I'm showing how easy it is to build a terrain. Again, very, very quickly here, as I move in here, you can see, again, I'm importing a bunch of contour lines. These contour lines, would be read in meter, and these contour lines, just a big bunch of contours. I am going to extract some points from these contour lines, and I explained that in some tutorials in there, how to do that. Basically, I'm breaking these contour lines into, say, 10-meter chunks. If these contours are somehow away from each other, say, like, they have a Z separation of 10 meters, say, I split these contours into 5-meter chunks, and I just extract the points that result from that. This is the points extracted from these contours. You can generate a mesh from contours very easily, but here I'm generating points from these contours, and then I generate the mesh from the points. It's a much faster process within Rhino. So I use this tool within Rhino, which is a Delaunay triangulator. So I'm going to, at this point, I hit my point, and I have now obtained a mesh using the mesh, this program here called Mesh Patch command, produced for me a topography. This topography is way too busy. There's too much detail. It needs to be defeatured. So, and we don't need all of it. We are defeaturing it by using a good tool in Rhino. Again, that's one of the powers of Rhino, is these surfacing tools that are available. I'm going to drape it, which is somehow similar to extending a silk sort of tablecloth on this. And this tablecloth stiffness can be controlled, and its weight can be controlled. And here is a sort of, you can almost see the gridding on this surface because these are the isoparametric representations on the surface. But this surface, this is what I'm going to be using for my BlockRanger. I extract its boundary and pull it down. And then, so now I look at it sideways, and I cut the lower part, trim it with a horizontal line that I draw arbitrarily, and trim the lower part of the lateral surface, the wall. And now I get something that kind of looks like a Flag3D model, except it has no bottom. You can see the bottom is open. So I join the whole thing into one single surface, which is not closed, and then cap it, and gives me now one single solid. This object is a single block that qualifies for BlockRanger because it has 6 faces. The top face is a complex face, but it's just one surface, one NURB surface, as they call it. And so now I go and click on the BlockRanger command, which is right here, and it gives me some parameters. I modify some of these parameters. By the way, I can export, Flag3D. I can export in a variety of formats: ANSYS, Abacus, Mark, Nastran, Patran, IDEAS. All of these formats are possible for BlockRanger. A Flag3D grid was generated, and I now read this Flag3D grid into Flag3D like this, and there you go. So it's relatively simple, but it's, it's exactly similar to a mesh that you would produce using, say, the topograph command that existed in Flag3D, or using fish. So it's not exactly groundbreaking, but I just want to show you how easy it is. This is a very simpler explanation. This is an example of some civil tunnel. I'm not going into the whole details, but I want to show you the block layout. Again, I created this solid. These blocks obviously have to respect the requirements, meaning that each face has to match another face. So you can see there is some work that goes into that. That's not automatic. So, and the number of blocks is somewhere in the order of 40, 50. And when you go past 1,000 blocks, it becomes extremely tedious. So you can see that these blocks are very carefully crafted by me in this case, but by you in the future. And then I click on BlockRanger, and I change some parameters. basically this is zone size adimensionally, so if you look at the length of the whole object, 0.1, the whole length of the object is the default zone size which you can modify. And I import this now into Factory. Okay, apologize for the disruption. We had a little adversity here with the network, which we seem to have corrected. So in that previous example, as I showed earlier, you bring in a collection of solids that I have already created. This particular solid is made in such a way that you can pile these layers one after each other and create some sort of a periodic excavation sequence. But you can see that these blocks are each individually kind of carefully built. It's a tedious thing, and again, some of them more modern 2.5D semi-automatic extrusions allow you to do this thing much faster, which we're getting there in a matter of a few months. We are working on the development on it with proven technology. But here I'm peeling off the various blocks here just to show you, and I have already organized these blocks into layers within Rhino. So each of these things that I'm showing here is a collection of multiple blocks. But my expectation is that once I read this into Flag3D, I will be able to see these as different groups. So this is how we kind of create a certain connectivity between Rhino and Flag3D. I select all the objects, and I click on BlockRanger, which asks me about a number of parameters, and I say that's fine, and computes the grid. When the grid is being computed, anytime you click on escape, it will stop, and it will tell you basically, how many blocks were good, how many blocks were bad. So everything is in front of your eyes. If there were blocks that were bad, they appear on the screen highlighted. So this is finally the grid that was generated. More tunneling examples. So essentially, this is BlockRanger at work within KubrixGEO version 14. You can see the variety of shapes that can be handled. Some rather primitive shapes, maybe for mechanical engineering applications, but for our area, where we have been more concerned about the physics of the problem, it's relatively new. But Flag3D is a program that has been around for a number of years and continues to grow. And little by little, we keep on adding new tools to make sure the program is better and better used. I would like to just give you a quick look to the future of BlockRanger. These are some examples of BlockRanger 2.0 prototype that we have been working on. Essentially, this example of a collection of intersecting tunnels is really obtained through a number of 2.5D extrusions, which I referred to. So in this tunnel, there's an extrusion that goes from this side all the way to this side, and then the extrusion. There are 3 different extrusions in 3 different directions. This other example is a bit simpler. We have essentially a more or less straight 2.5D extrusion here, but a 2D mesh is produced, automatic quad mesh 2D that is produced, which is sort of uses essentially a paving algorithm, advancing front paving algorithm, which is then produces a quad mesh, which is then extruded in an uneven way in different places to show these various drifts for a mining application that we have used this mesh for, actually. So this interactive meshing is a welcome tool to automatic hex meshing that adds really to the quiver of all tools that we have available. As again, many tools, none of them really fully ideal, and that's the nature of things. That's the dynamics that sort of keep us working as engineers. That you can improve things. You could always use KUBRIX auto meshing for doing everything, but it's not the appropriate tool. in some cases, and BlockRanger will be the right tool. And of course, there's always Flag3D, the fish command, and also the 2D extruder that is available in Flag3D is a useful tool for a large class of applications. Any of these commands can be combined. You essentially go from a Flag3D model that you have on your screen, and you can right-click on it and export that as a WRL, and immediately it becomes readable within Rhino, where you can do things to it, extract parts of it, clean it up, and generate a new mesh and read it back into Flag3D to replace an existing component in Flag3D. So these all work well together. And obviously, we have all these choices, but as I said, none of them are ideal. This is that tunneling example produced with BlockRanger here in the lower side. Unfortunately, the screen is not large enough to highlight the differences between these meshes clearly. But this is a BlockRanger, so some type of meshing that involved overall 8 to 10 hours of work in the creation of these assembly of blocks. This is tetrahedral meshing, the easiest one. You still have to create a closed non-manifold surface, so there is still work that goes into creation of these surfaces and so on, which represents about I would say 1/3 of what we did in terms of solid layout. This is the KUBRIX TET split meshing. Every hex has been broken down to hexahedron. Again, for regular finite element analysis, this is not a good type of mesh. For Flag3D, it works perfectly. It works quite well. This is what is obtained with KUBRIX auto-hex meshing. So that same non-manifold surface that goes into TET or TET split can be used to produce a nice hexahedral mesh. KUBRIX allows you to produce different mesh structures, and this last one is produced using a different mesh structure, which is, I think, Structical 4. Overall, the benefits of KubrixGEO is that it gives you a choice between interactive precision meshing and automatic hex tetrahedral meshing. And the automatic hex and TET have been enhanced. There's a faster TET and hex mesher in it, and there are some additional improvements in terms of fractures and faults that can now be within a hexahedral mesh rather than just a tetrahedral mesh as it was the case before. Also, KubrixGEO provides a smart sort of equilibrium between control and automation, which you always need. And that's not simply the case in geomechanics. It's true in various areas, whether it's electronics or aerospace or biomedical. There are examples that need control. There are examples that need speed. There are examples that are organic in shape. There are examples that are mechanical in shape. These are all have various treatments. And in this fashion, KubrixGEO can be the cornerstone of a reliable and cost-effective workflow in your engineering applications. Thank you. Now, my question to you is, do you have any questions? And I have some questions here that were posted in our okay, one of the questions that I have here, okay, I'm going to answer some of the questions here. One of the questions that was asked by one of the audience was, can a site be a curved feature? And I imagine that the question was asked earlier in the presentation. As you can see, it can. Not many sites can be curved, and many things can be produced. Will the Rhino layer be separated in groups in 3-deck as well? Okay. The 3-deck output is not yet available, but would be available in the release version, which we are hoping to do early in November. And in that one, yes, these will be different groups or different regions. I believe we are moving more towards groups. So we will have blocks that would be then composed of, or regions or groups that would be composed of blocks that then later on will be zoned. But these will be separated from each other, yes. I have another question here. What is the cost of KubrixGEO? I think the cost of KubrixGEO is something in the order of, in the US, the retail price is around $13,000. Can BlockRanger output 3-deck? That's a very good question. We have been kind of ambivalent about it, not because it can't be done, but because we were just, the demand was not as prominent as the demand for KUBRIX, in particular because we already have two tools that produce 3-deck models. One is an automatic tool within KubrixGEO, in which you define essentially your outer surfaces, and you rely on KUBRIX to fill the inside with tetrahedral blocks. We also have this sort of a free block definition within Rhino, which allows you to create essentially blocks within Rhino and export them as is. So you are totally responsible for the convexity of your blocks, and you click on that icon that has a little 3-deck sign on it. It produces a little file, and then you click on another function, and that produces a poly file in 3-deck. So this is yet a third way of producing 3-deck models. We're a little bit thinking and polling people on how best to promote this, or more exactly, how best to make this fit the way people work. And we will come to a decision very quickly and have that implemented. It's almost all there. It's just a question of what format we're going to put it out. Can BlockRanger be used with 3-deck? Again, that was the question that I was asking. How easy to generate meshes for irregular blocks in 3-deck? And again, as I said, there are already one automatic way of producing 3-deck blocks, which is KUBRIX automatic meshing. You define the entirety of your object as triangular surfaces, and anything that are in there, such as faults, hanging faults, etc., can be put in your model. There's a very clear procedure that is explained in the tutorials that shows how to handle hanging faults and intersecting faults. The model that is produced is a 3-deck model. It's a poly file, and the faces are indexed in such a way that you can easily recover in your 3-deck model all the joints that you defined in Rhino become joints in 3-deck with the right ID number that you can apply whatever properties you want to. And in fact, you do the same thing. They become face groups that then you can promote to interfaces. So this is already available in 3-deck. As I said, in terms of using it with BlockRanger, this will be clarified shortly. Is BlockRanger is compatible with other software? Yes, it is. In fact, the totality of the KUBRIX lineup, it can produce basically all the standard file formats that people use in computational fluid mechanics, structural mechanics, crash simulation, metal forming, biomedical engineering, electronics, drop tests in electronics, and all sorts of applications like that. All these are available. Okay, one of the questions was asked was how to make sure that the blocks and meshes correspond with each other, match each other in the output mesh. Obviously, that is a concern, although Stack 3D and both 3-deck allow you to do an attach. So if the blocks didn't line up, you could still attach them as long as they do come in contact with each other. But no, I guess the work is that when you assemble the blocks, it's really your responsibility, and the tutorials explain that in detail, that when you create one first block, the next block that will be neighboring it would need to use the same grid points, and the same edges, and the same surfaces. And that sounds maybe a little bit complicated, but in practice it's very, very easy, because Rhino easily provides ways to copy completely, extract a face from an existing solid, extract another face from an existing solid, and basically create a solid in sandwich between the two faces. So this becomes a moot point when you're working with Rhino. But yes, it's your responsibility as the creator of the block layout to make sure that these blocks share the same corners, edges and faces. Okay, how much, someone was asking me, how much faster is mesh generation in FLAG3D? How much does the use of BlockRanger speed up mesh generation in FLAG3D? This is a very, multifaceted question. If you want to create one cube, I think you can do gen cube XYZ, 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 and you got it. You have a cube. So by the time you fire up Rhino and click on BlockRanger and copy and read it into FLAG3D, that does it. But unfortunately, most engineering is not like that. And as a result, you need a whole array of tools that are available to you. As soon as you go to a slightly more complex shape, you may want to consider the FLAG3D 2D extruder, which allows you to really lay out your model on a 2D sort of a layer and then extrude that in one direction. That will give you a model that is readily usable in FLAG3D. As soon as your model is no longer just perfectly straight, or what people call as long as it's not a skyline model, then you have curved surfaces, and that's when BlockRanger comes in. You may want to use that as long as the number of blocks remain below a few hundred. BlockRanger is definitely the fastest way of producing models for FLAG3D. And then finally, as soon as you get to problems with organic shapes, topography, intersections, complex intersections, and so on, you get to the area where automatic KUBRIX meshing with all the options of TET meshing, hex meshing, octree meshing becomes the prominent way to do these things. Okay, I'm reading here some of the questions here that people have sent me. And okay, so for the discretization in finite difference within 3DEC, someone asked me whether or not this discretization can be produced by BlockRanger or by KUBRIX, I assume. Well, no, at this time, what we call mesh generation for 3DEC, it's really block generation for 3DEC, because frankly, once that block is generated, then 3DEC essentially subdivides that into different zones. This is almost part of the 3DEC solution algorithm. We somehow don't want to hear about the zoning within 3DEC. It doesn't really matter to us how 3DEC does that. That's what it needs to do to resolve that one block. So we don't look at it as mesh generation. We don't produce that. And then that's about it. I think I went through most of the questions. And if anyone has any other questions, I am completely available to you in the next few days. You can feel free to email me. My email is taghavi@itascacg.com, taghavi@itascacg.com, and I will be glad to answer your questions. Thank you very much for your attention, and have a great day. Bye-bye.